But in fact, if we use a finer scale decomposition of the work, you can see that the green chunks of data do not depend individually on all the red data. On a finer scale, you can see that we're actually free to do even more reordering if we're clever. And that way we reduce the amount of data motion we have to wait on. In particular, the green guy over there, say in that corner, in the middle there, only has to depend on that one red guy if we're using a 7-point stencil rather in 3 dimensions. And I've exaggerated here. Really, that green region is much, much larger. So there are actually pieces on the interior that don't depend on any red guys at all. Right? So, and also it turns out the optimal ordering of communication and computation, if you take them together, is difficult to predict. So one way is to deal with this problem is to do what's called virtualize the processors, to create the illusion of more processes than there are physical resources available. This has been used by others. It's used in CHARM and a number of other systems. When we do this, however, we make something more general. In particular, before, if each processor only had one piece of work to do, there was no question about which piece of work you gave it, because you always waited for all the red work to finish before you did a green piece of work. And the number of green regions there was matched to the number of physical processors. That's changed now. There are many more pieces of work to each processor, and you have to decide when to do which. It will make a difference. And as I said, the optimal ordering is difficult to predict. Okay? So the classic technique then is to divide up the work into more cores than there are processors, or rather more processes than there are cores. So there are 16 processes here, virtual processors for 4 cores. And then what we do is we use a system that virtualizes this. It's an automated process in the MPI implementation. For example, adaptive MPI. However, when I used adaptive MPI on an IBM SP3 system, there was a slowdown. It actually didn't realize performance. And the trouble is the following. When an MPI call blocks waiting for data, it will yield to another virtual process, and the schedule will pick another virtual process at random or using some heuristic. But often what happens is that process waits as well because its data isn't ready. The trouble is MPI doesn't provide you the information you need to know which is the next thread will have its data ready. And that's why we don't get any performance improvement, because we're constantly bringing new work into memory, or rather activating it, but immediately it yields the thread to a different process. So it's uninformed about the actual progress of the work. This is important because the switch can have varying delays. We can't predict when data will arrive. So we need to have some good knowledge about that in order to schedule these things intelligently. Okay? This is where a set of runtime libraries that my students are working on, called Time and Tarragon, in which we represent the program as a graph. So these are pieces of work coming from the Jacobi method in 3D. They're linked together by their common edges. We can see the relationship, actually in this picture here, there's a graph of sorts too. But we actually make that graph explicit in the program representation, and we keep track of when data arrives along an edge, so that when a task has all edges ready, it will be scheduled, and the schedule will know this and never try to schedule a piece of work that isn't ready yet. It's a classic technique coming from data flow. And the idea now is you've got a partial ordering of tasks. We don't say that this task has to come before that task, but rather that a bunch of tasks here can go in any order and they come before a bunch of other tasks. And so now the data motion and the computation are coupled activities. When a task completes, it fires and sends, or rather runs, it fires, and when it finishes running, it sends data along its outgoing edges so that other tasks will become aware of the fact that that task is completed and that they have received the data they need to run. There are background runtime services running as separate threads that keep track of all this, and they have very small overheads. And then the state, that is the information kept in the graph, allows us to know when the computation is ready. And we've got some encouraging results. I think I have about 5 minutes. Is that right? Okay. So I'll be brief here. I'll just look at one of the results. We ran on a couple of different systems. I'll look at Jacobi's method on 2 machines called Thunder and DataStar. Thunder is located at Livermore Lab, which has an Itanium with a nice quadric switch. And DataStar, no longer existing, but a Power 4 Plus system, had 8-way 1.5 gigahertz chips. And running on Jacobi's method, on Thunder, there are 4 implementations. The base implementation is what you do with a traditional MPI implementation, and the time version is the one using our runtime system called Time. We boost performance from 65 to 75 gigaflops on that machine. Ideally, that is, if we shut off communication and only run the computation, we go a bit further. So we got about half the communication back. And as the problem size gets larger, the amount of communication drops because the problem has what's called a smaller surface to volume ratio. Right? So eventually, of course, communication goes away. There's no advantage to overlap. And then similarly on the data star system, we also got an improvement. Not quite as much as on Thunder, and the reason is that on Datastar, the computation time is not as fast relative, the communication is not as slow relative to the computation, so there's less of benefit of overlap. We also got similar improvements, that's right, similar improvements with FFTs and also with Summa, but I don't have time to show that. We also got improvement with Tarragon. This is another system that at that time was working with fine-grained cell model simulations, and so we got a similar improvement. The speed up was on the order of about 30%. In this calculation, it was a bit better. But we don't want programmers to have to write using this data flow style of programming. The domain scientist really doesn't want to know so much about this, and only the hardy programmers who really take a joy in writing parallel programs. And we certainly recognize those users, but we realize that most users of cycles on large-scale systems aren't of that group. And so the question is, how can we get a task graph from an existing application? And the idea is, since most programs are written in MPI, and we send and receive messages telling us exactly who depends on which process, let's just use an MPI program to express that information. And so a new project, which has just received funding in a collaboration with Dan Quinlan at CASC up at Livermore, and also Eric Balaska at PNNL and John Ware at UCSD, is to use a translator plus some runtime support to extract the data flow graph from an MPI program. Because after all, the MPI program expresses all the data dependencies. And so this translator gives us the effect of a specialized programming language which understands the library calls in MPI, that is the sends and receives, and can actually generate code that helps us figure out this graph. All right? So I'll talk about that another day because it's a work that's just getting off the ground now. And so I just want to mention that Time and Tarragon are these 2 models for hiding latency. And they avoid some of the classic overheads in dealing with the latency hiding problem. This problem is actually ubiquitous. It is not simply one that's restricted to the MPI world. It will exist if you're using multi-core processors, a single one. It will also exist if you're using a hybrid system with a GPU accelerator. Who's used GPUs actually here? Anybody? A few, just getting started. Okay. The notion of a graph-based execution model has a rich history on shared memory systems, but there have been very few efforts that have actually done this on distributed memory. And then, of course, in addition to generalizing to hybrid systems rather with GPUs, multi-physics simulations where you have multiple coupled simulations are also useful because they have their own data transfer delays, but at a higher granularity. Okay, so I want to acknowledge the work of my various students. And also by collaborators involving these activities located in various places. Shing, your name isn't there. Sorry about that. Shing Kai is also a collaborator working with the student Dita Munat on the GPU. I'll be talking about that next week. And also acknowledge the support of various organizations who have helped make this possible. And just mention that this is my department, this is where I am, and if you ever come to visit San Diego one day, be certain to let us know. Mike is also here, and we're happy to visit you. And if you know of any students who are interested in our PhD program, let us know, because here are all my colleagues. We work in a number of different areas. We've grown quite a bit in the last several years, about 50 faculty now. And anyway, I'll leave that with that nice picture there. The weather wasn't quite so nice as that when I left, but actually it normally is that this time of year. Anyway, I appreciate getting a chance to talk to you, and if you have any questions, let me know. I'll be around for the week, so if you have a chance, we can chat then. Thank you.